Hi, welcome to the next lecture in the NPTEL course on Haskell. In this lecture, we will look at an important data structure, stack. Some of you who have already learned programming might have seen this in an introductory programming or data structure course. We will just see how to implement stacks in Haskell and we will look at a few applications. Okay, what is a stack? A stack is what is called a last in first out kind of data structure. The last thing that enters the stack is the first thing to get out. Okay, so that is what. So you can visualize it as some stack of plates kept on some kitchen counter. So if you want to take the top, if you want to grab a plate from the stack, what would you pick? You would just pick the topmost. And if you want to add a plate to the stack, you will just put it on the top, right? So that is the point. Both adding an element to the stack and taking an element away from the stack happens at one end. That is what it is, a stack. This is to be contrast with another data structure called queue, which we will see. Queue is also a very natural kind of data structure. We will see lots of real life examples of queues. You join a queue, the first person to join the queue will be the first person to get out. You join the queue at the end and people at the front get out and the queue slowly moves on. Okay, so that is a queue. We will look at stacks this time. We will also look at an important concept in Haskell called a module. Okay, we will see how you can define a module and what it is useful for. That is the content of this lecture. So let's imagine, instead of imagining plates stacked one on top of the other, we'll imagine a collection of integers stacked one on top of the other. So we need to give names for adding an element to the stack and for extracting an element from the stack. Push is the traditionally push is the name used for add an element to the stack, and it will be added to the top of the stack. Okay, so top is the one end where everything happens. It's just like a stack of plates. Pop is the name for removing an element from the stack. I say remove an element from the stack, but there is really no choice. Okay, like a stack of plates in a cafeteria, you just remove the top of this thing. Other things require more effort. You usually don't do that. And we've already seen something very similar to this in Haskell, namely lists, right? Because a list is either empty or it is of the form x colon x's. If you want to add an element to the list, the simplest way to do is, if you have already x colon x's, you do y colon x colon x's. If you want to remove an element from the list, you do head or whatever, but also you pattern match and you extract the first element, right? So stack is just, the behavior of stack is very similar to list. The top of the stack is the head of the list. So you can have a very easy implementation of stacks as follows. Stack is now a type synonym. Recalling that type is used to give a new name to an existing type. List of int is an existing type, so you can give a new name to it called stack. And push is a method that, given an integer and a stack, it will add the element to the stack. I said top of the stack is just head of the list, so you push of n st is just n colon st. Pop is the name of removing an element from the stack. So if you want to pop an empty stack, you cannot, so you give an error. And if you want to pop a stack n colon st, you pattern match, you just split n and st, right? So this is how you would very simply implement a stack. But this allows all kinds of operations other than push and pop. Okay, so this is the important point. You can always represent various data structures that you want as some lists or some variant or some things that you already have, but you want to provide what is called a data abstraction. And the data abstraction that you want to provide here for a stack is that these are the only two operations that are possible. You cannot sort of assume some internal representation of a stack and do all kinds of other operations like take n st, st1 plus s2, this is st2. This is like taking a whole stack of plates together and just putting it on top of the other. Maybe you are able to do it in a in a cafeteria, but in general we don't want to allow it. Okay, and you can actually replace an element in the middle of a stack by taking the top n minus 1 elements, replacing the element there or putting x there, and then retaining the elements below that on the stack. Okay, you could do all this. So what we want to do really, so this lecture is not about really implementing stacks. Implementing stacks is very simple. You can use lists to implement them, but to actually enforce this data abstraction. Okay. Okay. So then, if you want to do that, so then it is very natural. We already have seen user-defined data types. Recall that you can use the keyword data to define a new data type. Yeah. Unlike type, which only defines a synonym, new data type. Right, and you say data stack, this is the name of the type, and I said typically it is convention that you use the same name both for the type name and the constructor. If there is only one constructor, this is the data constructor or value constructor. Depending on the context, you would know whether you are referring to the value constructor or to the type name. Now, push is the same thing, except now you can think of this data constructor stack as a kind of wrapper that you put around a list of integers. So, whenever you want to do any operation, you have to take away the wrapper, do the operation and put back the wrapper. Okay. So, push is a function from int arrow stack or a stack. Push of x into stack x's, right? Stack is the wrapper. You remove the wrapper and you will get x's, and you do the operation, namely adding x before x's, then you put back the wrapper. Okay. Stack is a wrapper around a list of ints. Remove the wrapper, operate on the list, whatever you want to do, put back the wrapper. Yeah, so that is the sequence here. And similarly, you can say, oh, if I want to pop, if your stack is, if you have wrapped the empty list and that is the stack, then you print an error. Otherwise, if it's stack of the wrapper stack, and then you have the list which is x followed by x's, then what you can do is you can extract the x, produce it separately, and then the remainder of the stack is stack x's. Yeah, so x has been removed, right? Okay, so this is one step higher. Now what can you do and what cannot you do? Okay. Now the following will not type check. You cannot say take n st, you cannot do st1 plus plus st2, you cannot do take of n minus 1 st plus plus singleton list x plus plus drop n minus 1 st. We will check that all these things indeed work as we intend in a bit. Okay, when we actually go to VS Code and try to program all this. Right, and there is no reason why you should think of only a stack of integers. You can have a polymorphic stack. In a polymorphic stack, recall that this is the type constructor, in the sense that if you give it a type A, it will give you a type stack A. So, if you give it int, so stack can be thought of as some kind of function that takes a type and produces a type. For int, it will produce stack int. For char, it will produce stack char, etc., etc. This is the value constructor. And this is just a wrapper around a list of values of type A. Okay, and then the programming is the same, push, pop. You can also have some two auxiliary functions, empty, which produces an empty stack, and isEmpty, which checks whether a stack is empty or not. And the programming is very simple. Push of x in stack x's is stack of x colon x's. Pop of stack empty list is some error message. Pop of stack x colon x's is you extract the x separately, and then you provide, then you as part of the result you go x separately and stack x's separately. empty is just stack empty list, you are producing the empty stack. Is empty checks whether the list access is null or not. Okay. So, this is the next level. So, we have now tried to impose some kind of condition, so that this new type, the stack type, only allows these 4 operations. Okay. So, that is the nice thing. Otherwise, it is just a list. Okay. You are just enforcing that only these 4 operations are possible. Okay. Yeah. So, just to recall, the stack occurring on the left is not a type, it is a type constructor, and the for any type A, stack A is a type, and the stack on the right is a value constructor or a data constructor. Given x's of type list A, stack of x's is of type stack A. Okay. Okay. Suppose I want to sum all the elements of a stack. Sum stack of stack x's is sum of x's. How do I do this? Does it even make sense? What if I had a stack of characters? Then how do I sum them? Yeah. So, what is the type of sum stack? It is num A implies stack A arrows A, right? It makes sense only when x's consists of numeric elements. Okay. So, this is just how you can build stacks. Let us use stacks in an actual example. We have seen this example of a postfix expression and evaluating postfix expressions in an earlier lecture, where we directly used lists, but now we can actually use stacks instead of lists, just to make it clearer. Okay. So, we have a list of tokens, and this is what we did. Instead, what you could, so we had a list of tokens, and depending on what the tokens were all left of number. So, the token was defined to be either type token is either int, it is an either type, either int x sparrow x sparrow x. You either specify an integer by saying left n, or you specify an operator by saying right op. That is so you have a list of tokens, and what we wanted to do was, from a list of tokens you want to get an expression. So, the expression is just E, where you, so your step is a function that you use. Step takes a list of expressions and a token and produces a new list of expressions, and you use fold-L step empty list. Okay. This is the empty list of expressions. This is a list of tokens. What does step do? If my element is left n, it will just add val n to, val n is a type of expression, it will add val n to the front of E's. Otherwise, if you have exp1 and exp2 in your expression lists, and if you have right op, then you will pop exp1 and exp2 and you will apply the operation to exp2 exp1, okay, and then you will push back the pop and push op applied on exp2 exp1. Right, we expressed all this in terms of lists. Now you can actually explicitly express them in terms of stacks. This makes more sense, because now you, in the particular coding here, you have a list of expressions and you also have a list of tokens. It would be much better if you had a list of tokens and a stack of expressions. Okay. So, it is more transparent to use a stack instead of a list. Operations are restricted to push and pop. Okay. So, here we directly added, not here, directly use the colon operator, in our earlier solution. But if you could use the colon operator, you could use all kinds of operators, right? You could have put something at the very end of the list or whatever, right? So instead, if you just use stacks, you are restricting your operations to only push pop and empty and is empty, of course. Yeah, so here is our thing. So token list to expression is list of tokens to expressions. You do first of pop of st, where st is fold L step empty stack. Here is the empty stack, and list of tokens. So if you have the empty, if you have any stack st, and if you do, if you want to process left n, you just push val n to the stack. If you have to process right op, you push op applied on x2 and x1 on the stack s2, where st2, where x1 comma st1 is pop st, x2 comma st2 is pop st1. Okay. So you first do a pop and then you do another pop. Each time you do a pop, you save the expression in x1 and x2, and then you do the operation on that. Okay. Okay. Okay, so let's see how this is programmed in VS Code. Let's go to VS Code now and see how this is programmed. Yeah, so you have, so new type is a is an optimization when you have data and some type name t equals some constructor name c and some argument, single argument. Okay, so the data type t has one constructor with one argument. In such cases, you can use new type t. Okay, this is some internal optimization which we don't care about now. I mean, we care about it, which is why we are using it, but which we cannot explain now, doesn't matter. Okay, some Haskell treats new type better, but it's only restricted to these cases where you have a single constructor which has a single argument. Okay, that argument could be a pair. Okay, it is just that it should have a single argument, which could be a pair or tuple or whatever, right? Haskell allows all that. It shouldn't be multiple arguments. Okay, so that's new type. So let me go back to the code. Right, so now I have programmed push here. Push of x in stack x's is stack of x colon x's. I have programmed pop here. Okay, there is nothing very deep happening here. Let's just recall this example where you have exp is a type of expressions, value integer, value int, add exp, sub exp, mul exp, and div exp. These are all denoting, so this is a recursive data structure. An expression is either a value which is an integer value, or it is add applied on two expressions, or it is sub applied on two expressions, or it is mul applied on two expressions, or it is div applied on two expressions. Okay, that is the definition, and that is what we have coded up as this type here. Notice that I cannot do new type etc. here because this exp has multiple constructors. Okay. Okay, stack has only one constructor, even though it's polymorphic and so on, it's fine. We can still use new type. Okay, and now we have some show function for this, and these are two example expressions. Let me try to load this and check how these expressions look. Okay, x1 is 3 plus 5 times 2, x2 is 3 plus 5 times 2, notice the change in the order of evaluation. X3 is 22 by 3 times 4 plus 5, we are only concerned about integer division, so it's fine, and we are ignoring division by 0. Evaluation is just this, so eval of val n is just n, eval of add e1 e2 is eval e1 plus eval e2, and so on and so forth. Now token is of type either int x bar o x, so each token is either of the form left n where n is an int, or right op where op is of type x bar o x, and right now we have 4 ops here, okay, add, sub, mul and div, and so we had something where you convert a string to a token list. So if you see plus, you will say write add, if you see minus, you will see write sub, if you see star, you will see write mul, if you see slash, you will say write div, and you are supposed to be reading this, you are supposed to provide an input for this in postfix form. So okay, and then token list to expression will take a list of tokens and give an expression, and that is exactly the code that I showed earlier, right? And string to expression will take a string to token list, and then it will take that token list to expression. Finally, eval when expression string is, you provide a string, it will take it to an expression and it will evaluate it. So let's check how this works. So if I say, for instance, eval exp string, and I give something in postfix notation 2 5 plus, let's say, then it will interpret it as 2 plus 5, right? Remember, in postfix expression, you give 2 arguments first and then you give the operator to be performed on those two expressions, and postfix doesn't require parenthesis, as we already saw. Eval exp string of, if I want to say 2 plus 5 into 3, I will say 2 and then I will say 5 3 and then say star. The star will apply to 5 and 3, and then the plus, and then I will put a plus, the plus will apply to 2 and 5 star 3, okay. So in fact, rather than evaluating the expression, I should show the expression string to expression 2 5 3 star plus, right? It is 2 plus 5 times 3. If I want to say 2 plus 5 times 3, then I should say 2 plus 5, so 2 5 plus, and then put a 3 and then put a star. So this will say 2 plus 5 star 3, and yeah, so this tells you how to use stacks, okay. So and in fact, stacks are very closely related to your any computer architecture, because the order in which you make, so suppose you are working in some, even in Haskell, you make a recursive call, then the information related to the previous call should be stored somewhere, and it should be restored after this recursive call is over. The recursive call might have a recursive call of its own, so you will have a series of calls which will all be, information corresponding to each recursive call will be stored in a stack, so that when the latest call exits, it will go to the previous call, okay. So it is the last one that is added to the call stack will be the first one to be removed from the call stack, okay. So it is called call stack, and this is a very fundamental feature and fundamental cog in all architectures that we use in implementing languages, etc. And so stack is a very important data structure. This is one application of stacks, okay. Now after doing this, we will now show how to make this abstraction even better. I will go back to the slides now, okay. So if I have 2 stacks, let us say stack 1 and stack 2, I cannot do stack 1 plus plus stack 2 clearly. In fact, I should switch to VS Code and try this. let me reload this program, and then let me try stack 1 plus plus stack 2. I will get a type error because plus plus can be applied only on lists and not on stacks. Okay, fine. But you can actually write a function attach which will unwrap each stack and do whatever operation you want with those lists and then put the wrapper back on. Okay, and in fact, let me try to program this in VS Code. Attach is of type stack A arrow stack A arrow stack A, and attach of stack x's and stack y's is nothing but stack of x's plus plus y's. And I can actually now do attach of stack 1, 2, 3 okay, I cannot print it, it's saying, so let me I should say deriving show when I declare this thing. And now I can do this. Let me reload. Right? I can actually attach a stack 1, 2, 3 with stack 4, 5, 6 and I will get stack 1, 2, 3, 4, 5, 6. Now you might want this behavior, but this really doesn't feel like a stack because stack should only allow push and pop. How do you actually prevent a programmer from even reaching into the, because even though I put it as a data type and gave a type constructor and value constructor or whatever, you can still unwrap the wrapper, do whatever operation you want and put the wrapper back on. So it doesn't seem like we have provided enough protection. So let us get back to the slides and tell you how to do this. So you need a way to provide a precise interface for stack. Okay, this is the thing. The interface will tell you what exactly is allowed and nothing beyond this is allowed. And you need to hide the implementation. Nobody needs to know that stack is just a list. Okay, stack is a stack, that's all. The only way you can interact with the stack is push pop. We are able to do this attach kind of programs because we know that internally a stack is just a list, okay, with a wrapper around it. You shouldn't reveal that. And that is called abstract data types. And it is realized via a Haskell feature called modules. Okay, and it is important to discuss modules when we discuss data structures, because many data structures, the way you implement it, you want to provide it as an abstract data type. You do all kinds of algorithms inside it, but the user can use it only in some very precise manner. So ideally, you would like the internal representation to be hidden from the world. So the solution for that is to create a stack module. A module consists of functions that are related to each other. The name of the file must match the name of the module. The module can be used or imported in any other file in the same directory. Okay. So here is a stack module. So this is how you do it. You say module, that is the keyword, and you write the name of the module, and then you say what all functions you are going to export, and then you say where, and then you write your functions as usual. Okay, and I'll go to VS Code now and show you how we have done this module. Here you see that there is a function called stack.hs, which is the stack module. Okay, notice that I have done module and then push pop. I have a few extra functions as well. Top, which will remove the top element but not really remove, which will display the top element but not remove it. From list, which will convert from list to stack. Empty, which will create empty stack. Is empty will check whether the stack is empty. I am also saying stack here and then there is another stack there. We will come back to that later. But let's look at the implementation. The implementation is very simple. It is just the same old implementation. I have an extra show. I don't even want people to know that stack is wrapper around list. So a stack of x's is something like this. I will write each element of the list and put this vertical bar and then right arrow after each element. So you will see in a minute how a stack is displayed. So then you have push and pop, which is the same as the earlier. Top is the same as push pop, except it doesn't remove the top of stack x colon whatever is x. It doesn't return stack x's. Okay, stack x's would be the stack after returning x. You don't do that here. From list is just nothing. You are just from a list to a stack. All you need to do is put a wrapper. So from list is nothing but the wrapper stack. To create an empty stack, you just say stack empty list. Is empty is just checking whether x's is null. Okay, all the functionality is fine, but the extra stuff we are doing is to enforce some discipline as to how exactly you can use a stack. Okay, and how can you use a stack? For this, I need to create a new file. Let me call it use stack. Okay, I am calling it use stack. Okay, so now I should import. Just like you did import data.list.odor, I can just say import stack, and I can import whatever I want to use. So I will import all the things that have been exported from the stack module. I also had top and from list, right? So I can write whatever functions I want. I can say stack 3 equals from list of 1.10. Okay, so I can do all this in a different file, and if I now load this in GHCI, right, I get a problem. I'll explain why this problem. Okay, so this problem will disappear if I use from list here. Okay, so now I have loaded this. I can say stack 3. It's now printing because I have defined a show method for stack to do this. It is now printing it as 1 followed by 2 followed by 3 followed by 4. And it is some silly formatting, but you can change it to whatever you like. Okay, fine. So let me get back to the slides. So the functions and types listed inside the parentheses are exported. These ones. These ones are exported and they can be used outside the module, like we did. If you want to use outside the module, you have to import and then use it. But if it is not listed here, you cannot import it there. So you say module stack var and everything defined in the module. If you say module stack var without putting anything, any conditions, right, then everything defined in the module is exported. Here, so this is to control inside parenthesis, you control what is exported. sometimes you might have some features that are only used for your internal implementation purposes, which shouldn't be visible outside. So it is always useful to put these parentheses and control exactly what is exported when you create your own modules. Of course, when you import from somebody's module, you will specify exactly what all you want to import. If you say module stack and put empty parentheses, then nothing is exported. So now in use stack.hts I can do things like this: import stack, and I will say my stack is of type stack int, my stack is empty. Import stack will import everything exported by the stack module. Now remember that I'll go to Visual Studio Code now. Remember that in the stack module I exported one of these things, which is this, the type name. Suppose I didn't have that, suppose I didn't export that, and now I went to use stack. Let's try to, let me just say import stack without mentioning anything. Means everything exported by stack is imported here. Let's try to see what happens. Okay, it compiles. But suppose I wanted to say, oh, I have not given any types here. So let's give a types. Stack 1, stack 2 and stack 3 are all types of, all have type stack int, let's say. Okay, let me try to do this. Before we do that, notice here, when you are importing something, it will compile the imported stack module as well as your main module, okay, your main function, which is useStack.hts. See, so whenever you import something, whatever is imported will also be compiled. Right. So now there is a problem, because at this point stack does not export stack. I didn't put this stack inside the parenthesis, right? Earlier I had stack, and inside the parenthesis I had stack, and here I am mentioning stack, and it's a problem. And what is the error it is saying? It is saying type constructor is not in scope. Okay, so that is the point. So so this tells you that if I export all functions, but if I do not export the name stack, then nobody else can mention the name stack. Okay, recall that there are two roles played by the name stack. Stack is both a type constructor and also a value constructor. So when if you want to export the type constructor, you should put the name of the type constructor here. Yeah, so then everything is fine. Then you will be able to use the name of the type constructor here inside your use stack. Now it will compile. If I try in GHCI, okay, if I reload, yeah, now it compiles. So inside parenthesis you should export the name of the type constructor. But now let's try this. I did in use stack, I did from list of 1, 2, 3. Suppose I had just said stack 1, 2, 3. Let's see if it now compiles. It won't compile, because now it complains that the value constructor is not in scope really, because that stack that we mentioned here when you say stack int, that stack is a type constructor. When you say stack list 1, 2, 3, it is a value constructor, and we didn't export the value constructor. We only exported the type constructor. If you want to export the value constructor as well, then you should put one more parenthesis inside and put stack there. Okay, so stack is the name of the type constructor, and for that type constructor, all the value constructors that you want to export, you should put inside parenthesis here. Okay, and if you do that, then it will compile. Right, so this is the important thing. So you can export all kinds of functions, you can export all kinds of type constructors that you want to export, but for each type constructor, if you want to export certain of the value constructors, you can put those value constructors inside a further set of parentheses. Okay, let me return to the slides and where I explain all this. Yeah, here it's complaining that the type constructor is not available. Type constructor should be available because you need to be able to refer to the type. So you need to export the type constructor like this. So you will say module stack, and inside parentheses you will also export the name stack. Okay, fine. Now uStack will compile, but as I told you, if now I did new stack equals stack 0.9, it will again complain. It will say illegal term level use of the type constructor stack. I mean, it doesn't matter what the error message is a little inscrutable, but the point is that the type constructor has been exported, but yeah, so what it is actually thinking is that it is thinking that we are using the type constructor to build a value, because all it knows about stack is that it is a type constructor. So it is thinking that we are somehow trying to use the type constructor to build a value, and that is not possible. So what you need to do is, if the type constructor is not exported, it will say data constructor not in scope, because at this point it knows that, oh, you are trying to use a data constructor, but I don't know what this data constructor is. Okay, so you should test out all the various permutations and combinations here. Ideally, we should export the data, the type constructor, but not the data constructors. Okay, the data, or what I mean is the type constructor, and not the data constructors. So what we did in what I show in the previous slide, this is typically the correct usage in most cases. Because you don't want to explicitly export the value constructors, rather you should provide what are called smart constructors instead of what are smart constructors? They are nothing but functions like from list that we had earlier. They perform the same role as the value constructors, but you don't even want to reveal the name of the value constructors. Okay, that is what you are trying to do. And sometimes they will be smart because they will not exactly be the same functionality as the value constructors, but you might do a little extra work because these are separate functions. Okay, let us move on. So no one should be able to directly use the data constructors, rather they should use the smart constructors. You don't want them to directly use the data constructors because you don't even want to reveal that much structure about your type that you want to abstract out. If you want the data constructors to be used directly, you should do this stack. This is the name of the module. This is the name of the type constructor. This is the module name, and this is the name. This is the value constructor. Okay, so in stack of stack, the left stack is the export of the type constructor, and the right stack is the export of the value. On the stack within the parenthesis is the value constructor. In case there are many data constructors, we can export all of them by putting stack and within parenthesis dot dot. That will export all the data constructors that belong to stack. Okay, so this is just some operational details. Yeah, so you create this module and save it in stack.hs. You can also save some another thing called useStack.hs where you import stack, and if you load useStack.hs in GHCI, stack.hs is also compiled as we saw already, but we can only use the exported functions. So one flaw is that if you do not define a new kind of show, if you just said show push 5 empty, it will say stack and then list 5, then you might guess that the representation is just a list with some wrapper around it. Not that you can do anything with it, but you don't even want to reveal this, so you create a custom show. Okay, and for custom show, you have to say instance, as long as A is showable, stack A is also showable. You cannot do deriving, because deriving will give a default implementation of show. You want a custom implementation of show. So you should say, if A is an if A is an instance of show, then stack A is also an instance of show, and then you will say show of stack L is nothing but some fancy show, where fancy show is something like this. Okay, you use this function called intercalate, which will take a list of strings or list of lists and put your particular list in between any two lists. So if I have A, B, C, then this will give you right. So you had a list of strings and you intercalate one string inside them, means that you will get a longer list where this particular string is inserted in between any two elements of the original. Okay. So yeah, so that's it about stacks. Right. Finally, here is the stack module. You can do all this. Notice that exporting only the type constructor, not the value constructor. And this is a smart constructor. Provide a smart constructor. And hide the custom show to further hide the implementation. Okay, good. So now it might seem like we have done a lot of work for stack, but this is just to indicate how you can create your own abstract data type and implement this hiding. We will next look at a queue module. There you will see that actually you can vary the implementation, but provide a kind of a seamless interface. Okay, so that would be in the next lecture. Thank you.